there's an expression. Slow is smooth and smooth is fast. And in computation, we're always trying to go faster, particularly with today's AI revolution. But in our world, that quote should probably say flexible instead of smooth. And to dig up yet another famous quote, the only constant is change. And in computing today, change is coming fast and furious. So, what do we do if we want to design optimized systems, but also want to be able to turn on a dime when the next change comes along, like tomorrow afternoon? We need to design our systems with flexibility as a core principle. Hi, I'm Amelia Dalton, host of Chalk Talk. If we're designing systems that accelerate AI inference, for example, we need to do some serious optimization. But we need to do it in such a way that our work isn't obsolete before we even finish it. My guest today is Mike Fitton from Achronix, and we're going to talk about how new FPGAs and eFPGAs can give you the flexibility and power you need to go really fast and keep on going fast even as the game changes. All right, let's go. And before we get started, don't forget to click that link. There you can find even more information about this topic from Achronix. Hi, Mike. Thank you so much for joining me.
Hi, Amelia. How are you today?
I'm great. Thank you for asking. Okay, so we're talking about future-proofing compute acceleration with the help of FPGAs and eFPGA IP. Now, I have certainly seen a lot of growth in the FPGA market in just the last couple years. But Mike, how did we get to where we are today, especially in the realm of FPGAs?
So FPGAs have been around for a long time now, since the 80s, and they've gone through what we would say is 3 or 4 distinct phases over that time. So initially, they were mostly for glue logic. They were used for programmable I/O, and so they were really to kind of munge stuff together. Then it went through a second phase where they were used much more for FPGA connectivity. So this was connecting different chips with protocol like Interlock and connecting up Ethernet protocols, and so kind of future-proofing the protocols. Towards the end of that period, some acceleration started to be introduced as well. During this time, FPGAs grew in density and in performance. And that really led then to the third phase, which is somewhat where we are at the moment with data accelerations. You're seeing in the public domain, Microsoft talk about Brainwave, for example, for using FPGA for machine learning applications. There's also computer acceleration. SmartNIC is a frequent area where FPGAs are used. And then getting into the area of network function virtualization, where you can use a general purpose device like an FPGA for performing specific networking functions. And then finally, in 4G and now in 5G, FPGAs generally get used at the beginning of a deployment just because the ASICs aren't ready and it's much easier to do that kind of hardware acceleration in an FPGA. So we had that FPGA acceleration phase from 2018, and over time, the SAM, the service addressable market, has been increasing. We're now seeing a really interesting transition into what we're calling FPGA 4.0. So this is similar data acceleration, but it being done in a ubiquitous fashion. So as everything starts to push towards the edge, we can see that you get the same kind of machine learning applications need to be done at the edge, but that's in a different constrained form factor. So FPGAs might still be used, but they might be smaller devices, or they might be an embedded FPGA. Similarly, for aggregating IoT traffic, or for doing some of the 5G aspects, which could be integrated with an ASIC and done in, for example, the radio right at the edge. The final application there is FPGAs are used a lot in autonomous driving applications at the moment, but as those applications start to cost reduce and drive down in form factor and power, there needs to be much more integration, either then to smaller devices or to embedded FPGA IP. You'll notice at the bottom of the slide, there's 3 question marks for the SAM there. We're so early in this market. We've got some early indications that it's going to be big, but we really don't know how big. And so we're currently experiencing a really exciting time.
I was going to ask you about that, Mike. Okay, so I have chatted with you guys several times in the past, but for my audience who may not know, what are the biggest differences between FPGAs and embedded FPGAs, and what are the strengths of both technologies?
Okay, so you'll see on this slide, we start with a kind of classic FPGA, which I'm sure most people will be familiar with. This is the form factor most people have used up until now. Now that's being used as a reprogrammable workload accelerator. So you can reprogram it on the fly to do different things, everything from a virtual network function through to a machine learning application in the data center. Generally, we see deployments might start with FPGA because they're available off the shelf and can be used for lower volume applications. Sometimes they'll then be replaced by cost-reduced ASICs. And frequently, they're characterized by high-speed interfaces. On the Achronix product, we're supporting 100 gig SerDes at the moment with 400 gig Ethernet, and PCIe Gen 5 and the other FPGA vendors similarly are supporting kind of high-level interfaces in their roadmap. And then the final attribute there is high bandwidth memory is pretty typical. The newer kid on the block, so to speak, is embedded FPGA. So this is really just the same FPGA core fabric, but rather than being distributed in a standard product from us, it's enabled as an integrated IP core, a little bit like a CPU core that's integrated in within the rest of the SoC. That could be either integrated monolithically, so on the same die, or integrated as a chiplet, so an adjacent die in the same package. This is somewhat newer. There isn't a reason why it hasn't happened up until now, partly from process nodes that's driven down the size of it, so that's made it more amenable. And then classically, the traditional FPGA providers haven't wanted to support this IP because of the disruption it causes to the market. It's really exciting, really interesting application area, and that's why we're supporting it. It allows you a cost reduction from your standard FPGA that gives you a lower cost than a standard FPGA, but more flexibility than a traditional ASIC. So it's a nice place on the cost reduction continuum.
That makes sense. Now, Mike, what do the applications look like for both of these? I would imagine they overlap in some capacity.
Yeah, so that's a great point. If we look on the next slide, you can see on the left-hand side, again, the discrete FPGAs. And these are application areas. Traditional networking, we've gone up with several more zeros than we had previously, but we're now at 400 gig, going to 800 gig Ethernet and switching. But that's still often, from a volume point of view, is often more amenable to an FPGA than a custom device in that case. Data center, the volume is higher, but there's often different workloads. Different times of the day, you might want to be doing networking applications or cryptography or machine learning overnight. So there's different workloads that you want to accelerate. A dedicated accelerator for one isn't going to be able to support the other. So that's why we see FPGAs there. Similarly, in test and measurement, the volume is lower, but the requirements are really high, often using those high-speed interfaces. So on the left-hand side, you'll see those 3 or 4 areas that are grouped around there. In the center, we go through things that are sometimes deployed as discrete FPGA. Some of the machine learning algorithms could be a discrete FPGA, but then sometimes it's going to be integrated on the edge, and then it might be more appropriate to do that with an embedded FPGA IP. Defense applications don't have the volume driving them, but from a usability point of view, and particularly reducing the number of tape outs, we see embedded FPGAs being used in that space. And then the final one in the center here we have is around 5G, and particularly with respect to 5G, there was lots of discrete FPGAs used at the start. And as you can imagine, as the OEMs want to cost reduce those, they migrate further to the right-hand side, further towards an ASIC. And that's when you'll start to see embedded FPGA integrated in within a 5G ASIC to give flexibility just where it's required, but to be able to save costs and power with dedicated hardware functionality elsewhere. On the right-hand side, we see the areas where we think it's much more of a kind of a classic embedded FPGA play. This is where it's power constrained, it's where it's price constrained, or it's form factor constrained, or all of those. So that would be industrial. Automotive particularly is a good application of that, and we'll talk about that later on. Fintech's a little bit different. Fintech is much more about driving lowest round trip latency. And if you embed an FPGA, it's a lot easier way of reducing the tick to trade time. And so that's why we see it. That's another attribute of embedded FPGA, is you get much lower latency and much higher bandwidth between the different elements within the system.
So, Mike, what do FPGAs or embedded FPGAs really buy me as an engineer?
So as you'll see on the screen at the moment, we're showing kind of a classic ASIC unit volume graph. So this is something you're going to need to be doing millions of units to justify doing an ASIC in an advanced process node anyway. So this is pretty typical from what we've seen over time. If you add embedded FPGA, you can tape out earlier. What happens is the late changing requirements are absorbed into the programmable fabric, the reprogrammable fabric. And so that means you can solidify your requirements for your ASIC earlier. Therefore, you can pull the trigger on tape out earlier. Therefore, you get to market earlier. In addition to that, you can have a new FPGA image, effectively a new personality for that ASIC can be downloaded. It can even be downloaded on the fly. It can be deployed and you send out a new personality for that. That means you can address more product SKUs in that case. That's going to drive up the volume per ASIC. It's going to also decrease your number of tape outs. which is great at the moment with advanced process nodes and the really high cost of tape outs. And then the final one is you will see late changes be able to be absorbed into the reprogrammable embedded FPGA within that ASIC. That allows you to extend the product lifecycle and enable feature parity. If you're in 5G, for example, an operator is going to come in and request a new feature. If you've got some kind of programmability, you're probably going to be able to support that. If you don't have that kind of reprogrammable hardware, you're probably not going to be able to support that.
Sure, that really makes sense, Mike. So let's circle back to compute acceleration. How exactly do FPGAs fit into the picture here?
So what I'm going to do is I'm going to give you two different usage models. One as FPGA is a compute acceleration bridge. That's really like phase one or phase two FPGA. It's going back to our roots, back old school for doing munging the data together, just kind of getting that data off the interfaces. And then in a moment, we'll talk about the FPGA actually doing the guts of the processing algorithm. But to the acceleration bridge, you'll see on the slide in front of you, there's an ML ASIC at the top. So this could be a Google TPU, it could be the Habana device, could be GraphCore. There's a ton, it's like gold rush for ML ASICs at the moment. But oftentimes, they're quite dedicated functionality. They're really good at what they're dedicated to do, whatever kind of ML algorithm they've got. But they don't necessarily have the high-speed interfaces. They don't have the different flexible connectivity. And imagine if you're not sure whether you're going to deploy your ML ASIC into a smart factory, or you want to do it in robotics, or you want to do it in an autonomous vehicle, the interfaces you're going to connect to are all going to be different. So that means that using an FPGA here in the center is particularly good for doing the interfacing part. It could also load balance between different ASICs that you've got in that place. It can connect to a hosted CPU that you've got, and it could also do some pre-processing tasks. Something if you're doing, for example, autonomous driving, you want to do some sensor fusion, and you might want to do some pre-processing for doing your autonomous radar to be able to do collision detection coming up. And so there's some of those pre-processing tasks to be done in the FPGA as well. There's also some really nice ways of doing memory accesses. You can hang the memory off the FPGA rather than off the ML ASIC itself. That kind of future-proofs the ML ASIC itself and allows you potentially with using something like RDMA to have memory accesses to it, to external processing. And then the final point here we'll come back to in a moment is over time you might want to cost reduce this. So you could take the FPGA in the center and pull that in as an embedded FPGA within the ML ASIC itself.
Ah, okay. So, Mike, connectivity is a big part of any compute acceleration application. How can FPGA technology help me out here?
So what I wanted to do here was just highlight one of the interesting new trends for FPGAs to have a network on chip. So this is on the slide in front of you, you see the Achronix example. At least one of the other FPGA vendors has a slightly lower bandwidth NOC as well. The idea with a network on chip is classically, up until actually relatively recently, anybody who uses FPGAs will know that you build a design and you use about half of the logic just for plumbing, just for moving data from one corner of the chip to the other corner of the chip. It's kind of a waste of that processing resource. You can be doing useful algorithmic processing with that, and I don't want to be just moving data around. So what we've done in this case in 7 nanometer is we've added this dedicated network on chip. So you can see it's a bus. In our case, it's a bus 256 bits wide, giving you 512 gigabits per second in both directions on the columns and rows on the chip. The nice thing with that is it kind of offloads all of those resources you use for plumbing. They then get put onto dedicated lanes. And think of this like, it doesn't chop up the fabric, doesn't divide it up, but it's like a freeway that runs over downtown that you can use that freeway to access different portions of downtown, different portions of the FPGA without congesting the city's streets. In contrast, the traditional way of doing that kind of thing is you'd have a high bandwidth interface, GDDR6 or HBM2, and without a NOC, that's like bringing a freeway downtown and trying to terminate it at a stoplight. You're going to naturally get congestion. With a NOC, we can avoid all of that. It's got some great benefits with ease of design as well. It works directly out of the box. You don't even have to write a single line of RTL. You don't have to use any soft logic to connect up, for example, your PCI Express round to your external memory. Removing that congestion, remember that stoplight terminating the freeway. As we've removed that, that obviously eases time enclosure. That means you can hit a higher Fmax with the FPGA itself. And it also lends itself very well to things like partial reconfiguration where you want a very floor plan design. So that really helps. As I said, this is an IP that I expect everyone is going to be supporting in the future and is starting to emerge in FPGAs today. It can be deployed either in a standalone device or an embedded FPGA. And generally, when it's a larger embedded FPGA region, generally we encourage people to consider the network on chip because it offloads the processing quite a lot.
I can definitely see the power in there. So, Mike, I can also see how this would work for large scale deployments, like in a data center, for example. But how about at the edge, where we might still need some machine learning capability, but form factor, power, and price are constrained?
Yeah, so remember when I talked last slide about cost reduction, and particularly if you think about the applications diagram we had, there was on the right-hand side, there were some areas where you were cost constrained or you were power constrained or you were form factor constrained or all three. So in that case, what you might want to do is to integrate the dedicated engine for the matrix multiplication for ML, for example, here in the black on the right-hand side. So this could be a systolic array implementation that's got a bunch of int8 multipliers for doing really high performance matrix multiplication. So that's great. But just as we said 2 slides ago, the FPGA is actually pretty good for that IO adaptation, that classic data munging operation. And so then what we can do is we can integrate an embedded FPGA that supports the green functions, can then be monolithically or chiplet integrated with this high bandwidth matrix vector math engine that we've got on the right-hand side. And so then what that would be doing is IO adaptation for new protocols or emerging protocols or for different applications even. Data aggregation, a good example of data aggregation is when you've got autonomous vehicles, you need to do sensor fusion across lots of different platforms. So you've got LiDAR, you've got radar, you've got cameras, you've even got audio, and all of those different forms of data need to be fused together. They need to be combined before you start to do the processing. From one of the other really significant benefits we see as well is in this matrix compression block that you can see just before the black MVM block. Matrix compression, and you particularly see this in recursive neural networks where you're trying to do natural language processing, for example. As we talk, the vast majority of the data is zero. There's lots of gaps between the words. If you remove all of the gaps, if you don't process the data when it's zero, and imagine 90% of your data is zero, if you don't process that, you've got a 10x increase in the bandwidth that you can support coming through. FPGAs and programmable hardware in general are really good at that kind of compression and decompression algorithm, much more than the kind of dedicated systolic array architectures that would be an MVM. And so you're tailoring the different processing to the different bits and where it's most appropriate.
Okay, so Mike, I can see how FPGAs and eFPGAs can aggregate and bridge, but how about doing the machine learning inference processing? How can FPGAs assist me with this part of my design?
Great, and that brings us to the second application area that we talked about, Amelia, which was about using the FPGA for the actual processing itself. Now, as engineers, we have multiple different choices here, and I'm going to step through them a little bit. The classic way to do this is with CPUs, and CPUs is well accepted, have the most workload flexibility. You can easily change your software and do different things, but generally the power efficiency is less and the performance is less than competing solutions. Obviously, the CPU vendors are always investing in new application areas and they can start to accelerate this. But equally, generally, the accepted wisdom is you're going to get higher performance, for example, out of a GPU. Generally, a GPU has got higher performance and higher power efficiency, but is somewhat less flexible than a CPU. The programming model isn't quite as amenable, and we see that you have to do things in a slightly different way from a data flow perspective. So it's a different trade-off overall. If we go to a dedicated ASIC that we show here in blue, then you've got the highest performance you can expect, the highest power efficiency, but the least flexibility. Once you've dedicated an ASIC, for example, for machine learning inference, it's very, very difficult to repurpose it for something else. The final one, the FPGA and embedded FPGA, is kind of a compromise in these different areas. That what you get is pretty high performance, not quite that of ASIC, but approaching that of ASIC, pretty high efficiency overall, but significantly more workload flexibility. Remember what I was saying about an FPGA, you can use it to do virtual network function, you can do it to do machine learning, I can do genomics, I can do database search. There's a huge different wide application set that I can do from an FPGA point of view.
Very cool. Now, Mike, if I'm working on a machine learning design, DSP blocks can be very important. So, how do FPGAs and DSP blocks play together? And can I redesign my FPGA to make it work better for ML workloads?
Yeah, so what we're talking about here is bridging that gap we talked about from a performance perspective between the FPGA and the ASIC. And you can do that by tailoring the FPGA itself. Again, I'm going to give an Achronix example here, but you see this somewhat with other FPGA vendors as well about tailoring the FPGA architecture. What we did at least was we went back to a blank sheet of paper and we said, classically, the multiply accumulate block you have in the FPGA, the DSP block, is normally optimized for FIR filtering. So it's great for FIR filtering, but there isn't that many FIR filtering applications anymore. So it doesn't necessarily make sense to continue to optimize that multiply accumulate block for filtering. So what we've did instead, and what FPGA vendors in general can do, is to redesign that FPGA DSP block. And we redesigned it and we renamed it the machine learning processor, the MLP. We did this with 3 specific different things. We optimized the fact that when you're doing matrix multiplication for ML, the data is often quasi-static. It basically stays in the same place. Your weights stay in the same place. Your activation will frequently flow from one part of the systolic array to another. So you can exploit that. You can exploit the fact that the data isn't moving, because if we co-locate with a storage element with a memory block itself, that means I'm not having to use routing to connect up the two because they're co-located. I'm also not using power to move that data, and I don't have to reprogram the memory very often. So that just increases efficiency. It just makes it have more sense. If we also integrate the control here as well, everything is very close together. That means you've got a higher FPGA clock performance, a higher Fmax. And then also into this, what you would make sense to do is to support new different types of number format. So for example, in the Achronix block, we natively support block floating. So we support integer maths, we support floating point, but we also support block floating point, where you've got unique mantisses. There's a unique value for each sample, but you share an exponent across a block of data. What that does is it gives you performance which is approaching that floating point, but a much, much lower power consumption, with a power consumption and complexity of that of fixed point. So it's a good kind of trade-off, and particularly well suited for machine learning algorithms. We targeted this, and you will see later on that we've got the highest int8 performance with our new Speedster 7T device, just because of taking that blank sheet of paper and designing for how FPGAs should look for machine learning algorithms.
Now, Mike, this sounds great in theory, but do you have any real numbers to show the power of FPGA acceleration, especially for machine learning inference?
Yeah, thanks, Amelia. So we have got some numbers here. I should stress these are all public domain numbers from stuff on different people's websites. They're all using the same assumptions that you can see in the small text here about a clock rate and everything else, and using the DSP max or the MLP max for these kind of functions. In green, we've got the FPGAs, and in black, we've got kind of competing solutions. So here we've got examples from the Achronix Speedster 7T family, the Intel Agilex family, which is the first one out, and then 2 different families from Xilinx, the Xilinx Prime family, first one out, and then the Xilinx Versal AI family, which is partly colored black here because it's got some dedicated ML engines as well. So let's start at the top. You can see on the first row here, the Speedster 7T family has got the highest FPGA Mac performance. Kind of obvious that we should get that. We optimized for int8 and for block floating point that you'll see on the right-hand side. Intel made some different choices, and this isn't a criticism of any other vendor. They just went in a different direction. Intel has a lot more floating point capability, and so they seem to be steering away from ML inference applications. By contrast, Xilinx, again, not a criticism, but they, rather than investing in the DSP block with innovation, they added this AI engine, and that's why you can see here for int8 inference engine, you've got 133 TOPS for performance for there. The good thing about that, if someone wants to use that, they can get really high performance. They get very high performance from that. The challenge is it's not as flexible for different number formats, for example. So again, different choices for engineers depending on where they want to look at these different functions. And we're comparing these so you get an idea for an order of magnitude with some NVIDIA products here at the bottom. Generally, different applications are going to exert different requirements. And so relatively soon it will emerge whether you want the kind of high TOPS performance we talk about here, or you want a little bit more flexibility in addition to that.
Sure. Now, Mike, if I'm ready to get started, what does Achronix have to offer me in this space to help me along my way?
So let me talk a little bit about that. And so up until now, I've tried to be scrupulously fair to talk about FPGA in general and embedded FPGA in general, that any product you could get on the market. Specifically from an Achronix point of view, we support the Speedster 7T FPGA family. So that's a 7-nanometer family will be available towards the second half of this year. And that's also going to be deployed on this vector path accelerator card that we're doing with Bitware Molex. They're a great company for doing acceleration cards. It's really useful because that's oftentimes that someone can use the product and can even get deployed at scale in the data center. Somewhat uniquely for an FPGA vendor point of view, we also support embedded FPGA as well. So that means we have both the standard product and the embedded FPGA. It's going to be the same hardware. It's actually the same software, supports both. So that allows us to share engineering development across both and to support customers the same in moving their design from a standard FPGA to embedded FPGA. As you would expect, FPGAs are complex. You need a good technical support, and we've got a great partner ecosystem that you can see here as well and find on our website about people who can provide soft and hard IP to integrate with our products.
Okay, Mike, so can we dive in a little deeper about the Speedster 7T? What does it really buy me as an engineer?
Sure, thanks, Amelia. So the Speedster 7T product we've got here is built on TSMC 7 nanometer. As I said, the first product of that will be available in the second half of 2020. That's the Speedster 7T 1500 device. And I would encourage anybody who's listening to this to get in touch with Achronix to find out some more. From a high level point of view, we really built this product thinking about the three different pillars that you need to be able to do good compute acceleration in particular and processing in general. You need to be able to compute the processing element. You've got this really high bandwidth consumption engine that you've got. You need to be able to feed the beast with that. And so part of that is getting data onto the chip, but that's also getting data around the chip. So from a compute point of view, we've got those MLPs I talked about previously. So that's 40,000 int 8 max, which give you a total of about 80 teraops. The good thing about FPGAs is the effective terabits that you can use are very close to the actual number of teraops. It's very good with small batch sizes, for example, on FPGA. We also natively support floating point and block floating point just to get the efficiency from that as well. In terms of the data transfer, we've got these huge interfaces coming to it, 1.6 terabits per second of Ethernet bandwidth, PCIe Gen 5 and Gen 4, and we've got high bandwidth external memory with GDDR6. So that's great to getting the data on the chip, but in order to get the data around the chip, what we've got is this over-provisioned 2D NOC. So that's got more than 20 terabits per second of total bandwidth. That goes both around the FPGA core, but also permeates into the core itself. So that means you can connect up one region of FPGA core to another, or that region of FPGA core to one of the interfaces. And remember, we're offloading the FPGA resources. You don't have to use as precious soft logic resources for moving data around.
That makes sense, Mike. So let's talk a little bit more about your embedded FPGA IP as well. What's all involved in this IP?
So let's stay on the same slide for a moment. And just looking at the picture in front of you, imagine you can strip off all of the multicolored stuff around the side. And you're just left with the green core. So we effectively offer that as an FPGA compiler. So someone who wants to use the embedded FPGA that you see on the next slide, they basically get to build their own FPGA. You get to decide the resources, so the resource mix between logic, the number of memories that you have, even the size of the memories, what type of DSP block you've got, a FIR optimized one or a machine learning optimized one. So you get to decide anything that you want to about the FPGA fabric. It's almost like you're working in product planning here with Achronix, and you're defining what the product looks like for you. Then that IP gets integrated either monolithically with a GDS2 handoff, the SoC developer, or it can be chiplet integrated as a chiplet connected up with some kind of interface to a different die. The benefit of this is as you integrate the ASIC IP next to the FPGA core, you can be much more efficient with that. So any dedicated function that's not going to change, you should always put it in ASIC IP because the flexibility of FPGA comes at an overhead of larger die area. But that then leaves FPGA for where you really need to keep that flexibility. It could be in interfaces we've got here with sensor fusion, for example. You might have different algorithms for deep packet inspection or machine learning. So you're keeping the flexibility where you need it, but where the functions are fixed, you can also offload that into hard ASIC IP. And we even support the ability to have custom FPGA functions. You can define your own FPGA column. We support that with our tools. We integrate that with everything else. And that can give much more of an application optimized device. Could be great at doing data compression, for example, or it could be doing a TCAM memory access for different applications as well. So you have a very tailored FPGA architecture that's the right size for your application.
All right, Mike. Well, this has been a lot to take in today. Can you recap your main points?
Great, happy to. So just finishing up now, what we talked about today, and thanks for all the great questions, Amelia. We talked about FPGA and we talked about embedded FPGA. Taking it to that next generation, FPGA 4.0, where you see FPGAs deployed everywhere in the network, from the core all the way out to the edge. FPGAs there in both deployments are used to bridge data, so for aggregating data for machine learning, for example, but also to process data where it's necessary. It gives an alternative to dedicated machine learning ASICs that have more flexibility. It's also possible to optimize the FPGA fabric for compute acceleration workloads. Using a kind of a classic FPGA architecture that isn't optimized for it isn't going to give you as good performance as taking that blank sheet of paper approach and optimizing the performance in terms of teraops per second. And they're also optimizing the data movement with a high bandwidth network on chip. From an Achronix perspective, we're pleased to be able to uniquely support both standard standalone devices with Speedster 7T family and TSMC 7 nanometer, but also we support SpeedCore embedded FPGA because often a standalone FPGA isn't the right form factor for deployment, and then an embedded FPGA for integration into an ASIC SoC is oftentimes going to give that right trade-off of flexibility and power consumption and price.
Excellent. Well, I think that's all I have time for today. Thank you so much for joining me, Mike.
Well, thanks to you and thanks to everyone else for your time today.
And before we go, you didn't forget to click that link, did you? There you can find even more information about this topic from Achronix. For Chalk Talks, I'm Amelia Dalton from eejournal.com. For more Chalk Talks, head on over to the Chalk Talks section of EE Journal. You can't miss it, it's right across the top. Or head on over to YouTube, youtube.com/EEJournal.